we have looked at systems of the form y prime equals a times y, and we have used the eigenvalues of a to classify our equilibrium point y equals 0. Now we would like to use something called the trace-determinant plane to classify our equilibrium point y equals 0. So we're going to consider a 2 by 2 matrix of the form A, B, C, D. And then the trace of that matrix is defined to be the sum of the diagonal elements, which of course in this case is A plus D. The determinant of that matrix is AD minus BC. And so what we're going to do is rewrite our characteristic polynomial in terms of the trace, which we will call T, and the determinant, which we will call D. If we take the determinant of A minus lambda I, we will get A minus lambda times D minus lambda minus B times C. And then if we expand out, we should get lambda squared minus A plus D times lambda plus AD, and that's minus B times C. So in fact, our characteristic polynomial is lambda squared minus the trace times lambda plus the determinant. And so the eigenvalues of our matrix can be written in terms of the trace and the determinant. They are using the quadratic formula t plus the square root of t squared minus 4 times d divided by 2, or t minus the square root of t squared minus 4d divided by 2. And so we can classify our eigenvalues by looking at points in the trace-determinant plane. Here I've drawn two axes, the trace axis t and the determinant axis d, and then I've drawn the parabola d equals 1/4 t squared. And this is exactly where t squared minus 4d is equal to 0. So that's exactly where we get repeated eigenvalues. So we can break down this plane into cases. Okay, so first, we're going to look at the cases where t squared minus 4d is less than 0. This is where we end up with complex eigenvalues. In this case, the square root of t squared minus 4d is the square root of a negative number. That's going to give us our complex eigenvalues. In particular, we can even say that those complex eigenvalues are of the form t plus or minus the square I times the square root of 4d minus t squared over 2. So that if t squared minus 4d is less than 0 and t is equal to 0, then we get purely imaginary eigenvalues, and so we end up with a center. So here, when t is equal to 0 and t squared minus 4d is less than 0, that's where we end up with centers along the d axis. Now, if t is bigger than 0, then we get a positive real part to our complex eigenvalues, And so we can say that this is going to be a spiral source. And so here, in this area, we get spiral sources. And if t is less than 0, then our real part of our eigenvalue is negative. And so for those complex eigenvalues, we get a spiral sink. And so in this area of the trace-determinant plane, we get a spiral sink. So given a matrix, we can find the trace and find the determinant. And if we locate a point in this region here above the parabola d equals 1/4 t squared, so if we find a point in here or here or here or here, or maybe here, we end up with, say, a center, spiral sink, or a spiral source. Okay, now, getting some more cases in here, we have the cases where t squared minus 4d is greater than 0, so we get real eigenvalues here. In these cases, actually for all three of these cases, we're going to get real eigenvalues. So these will be real distinct eigenvalues. Here, my eigenvalues look like t plus or minus the square root of t squared minus 4d over 2. And if t squared minus 4d is bigger than 0, and our determinant is bigger than 0, and our trace is bigger than 0, in this case, we're going to have a nodal source, because essentially both of our eigenvalues here are going to be positive. You can see that because I'm going to take t, I'm going to add to it t squared minus, or the square root of t squared minus 4d. And of course, that first one will be positive. But also, when I subtract t squared minus 4d, I will be subtracting something that is less than t. So the square root of t squared minus 4d, if the determinant is positive, is going to be less than t. And so I'll subtract something less than t, and that again will give me a positive eigenvalue. So I will get a nodal source. Now, if t is negative, then and the determinant is still positive, then I will end up with a nodal sink for the same reasons. And so what we can do is we can go to these regions on our trace determinant plane, and here where the t is positive, but t squared minus 4d is positive, I'm going to get a nodal source. And here I'm going to get a nodal sink. Finally, when the determinant is negative, if the determinant is negative, then t squared minus 4d has to be positive. But not just positive, the square root of t squared minus 4d is actually going to be bigger in magnitude than t, and so I will end up with one positive and one negative eigenvalue. And so it is when d is negative, our determinant is negative, that I will get a saddle. And so all below the t-axis, I will get a saddle. Now, the only case that I haven't labeled is when t squared minus 4d equals 0. Those don't have official labels. I like to call this the repeat source, meaning repeated eigenvalue that is a source. And I like to call this one the repeat sink. Because again, the repeated eigenvalue is negative, and so it's a sink. And so again, instead of finding eigenvalues and eigenvectors, we can find the determinant and the trace of that matrix, which is a little bit simpler, and use that to determine whether our equilibrium point is a source or a sink, and whether that's a spiral source, a spiral sink, a nodal source, and a nodal sink, or is a saddle point. I think it's worth noting essentially that the repeat sink is essentially a very particular value that's right between the spiral sink and the nodal sink. And the repeat source is that very particular value that's right in between a spiral source and a nodal source. And so what we can do is we can look, say, at our phase plane. And so I'm going to go to phase planes in slopes, and we can look at, say, when there's a repeated sink, and I can plot a couple solutions like those. And what you see is that solutions are approaching 0, 0, but they always stay kind of to the left or the right of some dividing line. Let me see if I can get that dividing line in there. So they always stay either to the left or the right of that dividing line. But if I move just slightly off of that repeated sink, let's say we do negative 2.5, okay, for our parameter b, then all of a sudden now they're spiraling around, okay? And now we no longer have that repeated sink, but in fact we have a spiral sink. So I can go back again to the repeated sink, and you can see where solutions stay kind of on one side or the other of those lines, and they don't spiral around. If I move off, then they spiral around.